So, now I am going to branch out and discuss an application of the calculus of variations, namely the application in optimal control theory. Now, we will see that in this example, more often than not we are going to deal with functionals which has convex integrands. So, solving problems in optimal control theory will be a subset of whatever we have seen so far in terms of optimizing a functional. Okay. So, what is this optimal controls subject. So, calculus of variation in optimal controls. Okay. So, let me so what is this optimal control? So, it is a branch of applied maths, it is a branch of applied mathematics which deals with finding a control law for a dynamical system over a period of time. Notice now we are going to deal with systems which have some physical significance. So, now my independent variables are time instead of t as in the previous discussions. So, time such that an objective function is optimized. Okay. So, that is what we typically do in problems related to optimal controls. Okay. An example could be our dynamical system could be the spacecraft, and the objective function is to reach from the earth to the moon in the shortest possible fuel consumption, and the controls could be the various switches in the spacecraft, for example, the controls leading to rocket thruster and so on and so forth, right. So, this is a very simple example. As I said, the dynamical system could be our spacecraft, and my objective function could be to reach let us say from the planet earth to moon with minimum fuel consumption, and my controls could be the switches in our spacecraft, right. So, the controls are the switches in the spacecraft. So, it is the controls which determine which, or it is up to the user which has to determine when to switch on which switch. Okay. So, switches in the spacecraft, for example, the rocket thruster. Okay. So, what have we got here? So, well, another dynamical system could be the nation itself, and let us say the objective function is to reduce unemployment, and the controls could be the monetary and the fiscal policy. So, which means the current topics of reducing unemployment could possibly in our country could possibly be tackled with our optimal control setup. So, let us now formalize our definition in the form of a mathematical statement. Okay. So, formal or mathematical statement. So, so let me call this as the problems in optimal control as OC. So, from now on I am going to denote the optimal control problems as OC. So, the OC problem is to find the optimal control U star of t, where I am going to denote star as my optimal optimal or extremal functions, right. So, I am going to denote them by star, which causes the linear slash nonlinear time invariant system. The system is denoted by the ODE, which is x bar dot is equal to f of x bar comma u comma t. I denote my time invariant system, let us call it by 1, and in physical terms I call this system 1 by Planck. I denote my time invariant nonlinear slash linear in system by Planck, such that it gives me my optimal state x star. To give the state x star that optimizes the general performance index known as the PI performance index. Let me call this as PI, and the index is given by the functional. So, I denote this by my expression 2. So, my performance index is given by the functional j of y, which is given by s of x of Tf x bar comma Tf. So, this is my function plus integral from T0 to Tf v of x bar of t comma u bar of t comma t dt, right. So, notice that in the mathematical terms we are trying to optimizing the functional given by 2 subject to a non holonomic constraint given by 1. So, the answer is we have to find these functions u given the constraints 1, so that the objective function 2 is optimized. Okay. So, this is our performance index with some constraints on controls on the control variable, with some constraints on the control variable u of t and or x of t, such that the final time t of f may be fixed or it is free. The final time T f may be fixed or free, and the final state x bar of T f is the final state is denoted by x bar of T f. Okay. So, this means, so we have basically introduced some physical terms so far in our calculus of variations notations here. Okay. So, now my objective function is denoted by performance index, I denote it by Pi, and my constraint is denoted by my Planck condition, which is the non holonomic constraint or the differential constraint. Okay. So, the OC problems are going to be studied in 3 stages. They are studied in 3 stages. We will see that the step by step solution methodology follows very similar to the solution methodology of constraint optimization with non holonomic constraints. Okay. So, it is solved in 3 stages. So, stage 1. So, stage 1 we have to find the unconstrained optimal control or optimal solution. Optimal means the extremal, and when we look at convex integrands, this extremal is the minimal. So, optimal or the minimal solution to the objective to the objective function, right. Notice that the only point of complicacy or the complication in our objective function is the introduction of this function s or the cost function, but later on we will see that we can also absorb this function s inside our integral. We will do that shortly. So, we have to find the optimal solution to the objective function, one using calculus of variations. So, stage 2 is we are going to bring the system. So, our objective function is yeah. So, this is, let us go back, our objective. So, we have to find the unconstrained optimal solution to the objective function. The objective function is the functional itself, right. So, this is 1, the performance index is 2, and yeah. So, my objective function is 2 here. So, that is what my functional is. Okay. So, we bring the system 1, which is our constraint, and address the problem of finding the problem of finding the optimal control, which is our function u star of t, the optimal control which drives 1, and optimizes the objective function 2, okay. Drives 1 and optimizes the objective function 2. Okay. And finally, the stage 3 is we impose constraints on controls, and states to obtain my optimal control solutions, right, to obtain my optimal control solutions. Okay. So, let us see what is this 3 stage solution methodology, but before that let me reduce this performance index in a form that we are familiar with. So, what I just the following. So, we are going to look at the solution of optimal control problems purely using variational techniques, right, because this is a course on calculus of variations and not optimal controls. So, the problem is, let us now note, we note the following. Note that this particular quantity, the integral of t0 to t1 of ds dt of x bar comma t of dt, this is going to be integral. So, this is a perfect derivative. So, this will be s of x f comma t f minus s of x 0 comma t 0, right. Let me call this as 3. Now, what is this function? So, in physical terms, this function s is known as the cost function. This cost function objective function was introduced as early as in 1913 by a Russian mathematician named Bolza. So, when we introduce this cost function, this objective function including the cost function is also known as the Bolza problem. Okay. So, what I just said, so just a bit of trivia. So, this cost function s of x bar of t f comma t f, the introduction of this cost function is also known as the Bolza problem, first introduced in 1913. Okay. Okay. So, then let me use 3 and modify and write down the modified performance index or the objective function. Let me denote it by J2 of u bar of t. I see that this is nothing but the integral from t0 to t1 of, well, the original objective function involved v, the new objective function will involve v of x bar comma u bar comma t plus the derivative del s del t dt. So, now we have absorbed the cost function inside the integral, but it turns out that this functional is slightly different from our original objective functional or the performance index. Notice that this is also equal to j of u bar of t minus a constant which is s of x of t naught comma t naught, right. Okay. We call this expression of J2 by 4. Now, notice that the objective function j and J2 they only vary by a constant, which means that the optimal solution to j will be identically equal to the optimal solution to J2, right. So, what I just said is the following: the optimal solution to j or J2 are equivalent, right, and hence the optimal control problem can either be found from optimizing j or J2, right. So, that is one observation, and but if we were to find s, the optimal cost, we can only find it from our j, right. So, but the optimal cost is found, the optimal cost is found using j, right. And also further note that the time derivative of s of x bar comma t comes out to be, so this is something which is pure chain rule, and we will be using it shortly in a little while. So, this is del s partial derivative with respect to x plus, well, times x dot of t, the dot represents the time derivative, plus partial s partial t. Okay. So, we will use it very soon. Okay. So, now I am going to highlight this 3 stage methodology of the solution to the optimal control problem in a step by step format. Okay. So, let us write down the steps. In this lecture I am going to write down few steps. So, steps for solving optimal control problems via the calculus of variations. So, we will see that if we follow the step by step methodology, then almost all the problems in this topic are going to be solvable. Okay. So, the first step is we assume optimal conditions, right. So, which means we assume that the optimal values x star slash u star, we assume the optimal values for x star slash u star for the state variables, these are my state variables, and for my control variables respectively, right, and now we set up the objective function j of u star to be, so this is to be the J2 of u star, the second format, from T0 to Tf of v of x star comma u star comma t plus ds dt of x star, okay, dt. And then the second stage of this solution methodology is we take the variations of the controls and the state variable. So, take variations of the control and the state variables. Okay. State variables. So, which means let us fix at one point, let us say x bar of t naught is x naught, and we are going to consider our perturbed state. So, let the perturbed state and control variables are as follows. So, x of t is equal to x bar of x star of t plus delta of x bar of t, and u bar of t is equal to u star of t plus delta of u of t, right. Okay. And then so we can write down our perturbed quantities. So, my plant condition which was the non-holonomic constraint, one reduces to the following for the perturbed variable. So, which is x dot star plus delta of x dot gives me f of x bar star plus delta of x bar comma u star plus delta of u bar comma t. So, that is my plant condition, and my objective function, which is my performance index, is now going to be written in the form. So, j of u bar is integral from t 0 to t final plus delta t f. Note that we allow my final time step to vary, keeping the initial time t naught to be fixed. So, of v of x bar star plus delta of x bar plus comma u bar star plus delta of u bar comma t plus ds dt of this whole quantity integrated with respect to t. And finally, we are going to solve these constraint problem by introducing the so called Lagrange multiplier function, also known as the co-state vectors. So, I am going to write down the final step in this lecture. This solution methodology will continue in our next lecture. So, the final step is introduce time invariant system as well. The system is 1, which is my plant condition, time invariant system which is 1 as a constraint via the Lagrange multiplier method, right. Let me call this as lambda of t, also known as the co-state vector. Okay. So, that is my Lagrange multiplier function. Okay. So, we are going to let me introduce the augmented performance index with this constrained situation. So, my augmented or my constrained performance index. So, these are all the new terms, but the mathematical equivalent of these new terms are something we have already looked at in our previous lectures. So, the augmented performance index at optimal conditions are given by, let me denote this new functional as J A of u bar star. This is given to be the integral from t 0 to t f of v of x bar star comma u bar star t plus the partial s partial x dot x. Well, now I have used our chain rule. So, this is times x dot star, this is evaluated at the start condition plus partial s partial t evaluated again at the start condition. Okay. So, this quantity is nothing but the total derivative of S with respect to t evaluated at start condition. So, this quantity plus lambda of t times f of x star comma u star comma t minus x bar star. So, that is my this quantity inside this curly bracket is my non-holonomic constraint. So, let me just use a slightly smaller underlining mechanism. So, this is this. So, I have now introduced. So, this is a grand bracket, and now I have introduced the plant condition inside this functional, and now what we do is my perturbed, this is the final statement, my perturbed augmented performance index can now be written as follows. So, J A at any perturbed value u bar turns out to be integral from T 0 to T f plus delta T f of V of x bar star plus delta x bar comma u x bar u star plus delta of u bar comma t plus partial s partial x evaluated at the start condition or the optimal condition times x dot star will become x dot well the condition x dot start plus delta x. So, we are perturbing about. So, this is the perturbed augmented performance index about the point x star and u star. Okay. So, comma. So, this is my perturbed point plus the partial s partial t evaluated at the start condition, and finally plus my constraint lambda times f evaluated at x bar star plus delta x bar comma u star plus delta u comma t minus this condition which is perturbed now. So, x bar star dot plus delta x bar well the original value was at dot. So, we put a dot here as well as a dot here, okay. And that completes this whole description completes our step 3. So, in the next set of steps and in the next lecture I am going to introduce, well we have already seen that I am going to introduce the difference of the perturbed value with the original or the extremal value, and then from there we look at what is the first variation of from this difference, and from there we find the optimal control solution u star and the state variable x star. So, thank you very much so far for listening. So, thanks a lot.